We are going to start with chapter 10, which is on sequences and series. Now, this is going to be quite a bit different from what we have been doing. We have essentially been working on integration, and suddenly you will find stuff that does not seem to be connected to integration, but later on, hopefully, you will see the connection. So, the first two sections are on sequences. Now we are not going to spend too much time on sequences because we really need only few aspects of it in this particular course. It's a pretty extensive topic, and there are other courses where you would study much more in this area. So what is a sequence? Well, here's the definition. A sequence is an ordered list of numbers. So in other words, we write them as an, and then you have these brackets around it, and then you have the index n going from 1 to infinity. So this could be, for example, a1, a2, a3, and so on. A specific example could be 1, 1/2, 1/3, and so on. Now, sequences are generally written in two different ways. Obviously, this is the explicit way of writing it, but otherwise, there are two general ways. One is in recursive form, or also called recursion formula, and the second way is to write it in or as an explicit formula. So in this course we are going to spend time only when things are written in explicit formula in this form. So for example, one could write the sequence that I just wrote, n from 1 to infinity, as 1 over n in this manner. And in a simple way, one could just say an is equal to 1 over n. Now, the indices are also not written very frequently. For example, we need not write n going from 1 to infinity here, because it's almost always n is from 1 to infinity. Sometimes we have like an where n starts from 0 to infinity, and that at that time we would be very specific. So let's look at some examples of it. So here is another sequence where the sequence is 1 over 2 raised to the power n. So a1 is half, a2 would be 1/4, and so on. So here is a graphical representation of a sequence. So let's look at some sequences. So suppose I have an to be square root of n. Now notice I don't have to write the limits of the sequence every time. So we assume that it is from 1 to infinity even when I don't write anything. So this gives me a sequence with terms that are 1, square root 2, square root 3, and so on. Similarly, let's look at another one. Suppose I call it AK, and that is k minus 1 over k. This would be, now again k starts from 1, so if you put in 1, you would get 1 minus 1 over 1, which is 0. Then the next one would be 1 over 2, then 2/3, then 3/4, and so on. Another one, so suppose I have negative 1 to the power n times 1 over n. Now this one would be, when n is 1, I'm going to get negative 1. When n is 2, then I get negative 1 squared, so that makes it positive, and I get 1/2. The third term would have a negative sign, and it would be negative 1/3, and so on. So these are some typical sequences that we could encounter. Now, what is it about sequences that we really want to study? So the main thing is to study what's called the limit of a sequence. So let me read this paragraph first. If the terms of the sequence approaches a unique number L as n increases, that means that an can become arbitrarily close to L by making n sufficiently large. Then we say that limit an is equal to L exists and the sequence converges to L. In other words, as n increases to infinity, we say limit n going to infinity an is equal to L if the terms approach L. Now, if the terms of the sequence does not approach any single number as n increases, we say that the sequence has no limit and the sequence diverges. So when this happens, it converges, else it would diverge. So first let's look at it graphically, and then we will do few examples. So let's look at this particular sequence. So it is negative 1 raised to the power n divided by n squared plus 1. Now the first term is here, the second term is here, third is here, and as you just can see by looking at the graph that this clearly converges to 0. So as n increases, you keep getting closer and closer to the x-axis. So that means L, the limit, is 0. Other way to write it is limit an as n goes to infinity, which means limit n going to infinity of negative 1 to the power n 1 over n squared plus 1 is equal to 0. A sloppy way of writing the same thing is that an approaches 0 as n goes to infinity. but this is a more precise way of writing it. Let's look at another example. So here we have a sequence an, which is cosine of n pi. Now clearly, as n starts from 1, first you would get negative 1, and then when n is 2, you're going to get 1, then n is 3, you're going to get negative 1, and then 1, and so on. So as you can clearly see in the graph, that as n goes to infinity, the terms of this sequence does not approach any number. It keeps alternating between negative 1 and 1 and negative 1 and 1. So that means this guy diverges. Let's look at another one. So here we have the sequence as 4 n cube over n cube plus 1. Now you can clearly see from the graph that as n increases, we are approaching this line 4. So we don't really have to write down all the terms, and very soon we are going to see how we can find the limit without really graphing them. But here L is 4, as you can see graphically. Now let's go back and look at some of the examples that we just wrote a few seconds back. So the one that I wrote was a sequence square root n, which was 1, square root 2, square root 3, and so on. Now clearly, if you think about it, as n increases, this is just going to go and increase to infinity. So therefore this one diverges. The next one we looked at was n minus 1 over n, and the terms were 0, half, 2/3, 3/4. Now this converges, and we can see very soon that it will actually converge to 1. So therefore L is 1. Similarly, negative 1 to the power n, 1 over n, was negative 1 half, negative 1/3, and so on. Now if you were to graph it, you will see that this converges to 0. So the limit of this sequence is 0. Okay, so then next we are going to see how do we find these limits, and that is the most important thing.